Hi there. We're going to go over the quiz that we had on LeChatlier's principle and what we call more complicated equilibria problems. So let's just get going on that. So we have an equilibrium here. C plus D is an equilibrium with E plus 2F. So C plus D equilibrium E plus 2F. It says gaseous, so that means everything's in the gas phase. And we're told that the K, which is presumably KC, the way the problem is written here, is 3.0. So it's KC. Now we have a 2-liter flask, so our concentration of C is going to be 1 mole over 2 liters. That's 0.5 molar. Our concentration of D is going to be the same. Our concentration of E is going to be the same. F is going to have a concentration of 3 moles per 2 liters, and that's going to be 1.5 molar. So what we're going to do is calculate the value for Q. So for this equilibrium, Q is the product concentration, so E raised to their coefficients to the first, so F is going to be squared, and then C is going to be on the bottom and be to the first, and D is on the bottom to the first. Products over reactants, everybody raised to their coefficient. And now if we use the values that we have here, E is 0.5, F is 1.5, and that's going to be squared. C is 0.5, and D is 0.5. Okay, so we can plug and chug. We can simplify it a little bit. See that one of those 0.5s on the top and the bottom do cancel out. So 1.5 squared divided by 0.5, that gives me a Q of 4.5. That's greater than 3.0, which is the KC. Now, what does that mean? That means that the stuff on the top we have too much of. So we got too many products, so it means it's going to shift back towards the reactants to get to equilibrium. So if we look at the choices, that means proceed more rapidly to form the reactants C and D. So A was the correct answer to that. Moving on to the second question here, we have an equilibrium, and we're asked about the effect of removing some of the product, right? So product is being removed. That's at equilibrium, and what's going to happen is that we're going to have some of the reactants decrease, and the decrease is not going to be equal, because the second thing there, SO2, is going to decrease twice as fast as O2. Kind of goes back to the rate of reaction thing back in chapter 11, negative 1/2 delta SO2 delta T is equal to negative 1/1 delta O2 delta T, which means that the rate at which SO2 is changing is going to be 2 times the rate at which O2 is changing. If we cancel those negative signs out and multiply both of them by 2. So the correct answer should be this one, that SO2 decreases more than O2. Again, we know that the reactants are going to produce some more products to replace the SO3 that's been taken out of the system. Question 3, we're asked to look at these reactions and say where an increase in total pressure at constant temperatures will favor the formation of the product. So again, the rule is that if you increase pressure, it's going to shift to the side with less moles of gas. Okay, it's generally what will happen. So if we look at the first one there, we have 3 moles of gas on the reactant side, 2 moles of gas on the product side. That looks promising. If we look at the second one, it's 1 mole of gas on the reactant side, 2 moles of gas on the product side. If we look at the third one, it's 2 and 2. And then if we look at the last one, it's 0 and 1. So the only one where the number of moles of gas goes down is the first one. So that would be the correct answer. Looking on to chapter 4, we now have an exothermic reaction. I wrote out delta H instead of, since I could do the symbol very well there. But we have this equilibrium here forming ammonia from nitrogen and hydrogen. And it's exothermic. It gives off heat. That means heat is a product. So if heat's a product, if we go from 400 K to 800 K, we're increasing the temperature. If heat's a product, that's like adding product, so that's going to cause a shift that way. K will be less because we're making more products and less, more reactants and less products. So the answer is less than 0.53 would be the answer for that one. If delta H had been positive, that heat would have been a reactant and the equilibrium constant would have gone up on increasing temperature. That, incidentally, is frequently you'll see discussions about this equilibrium. It's very important. It was very important to the continuation of World War I past the first year, and because you need to make explosives with nitrates, and you can make nitrates from ammonia. And nitrogen, of course, is the principal component of the atmosphere. So if you can make this work and make ammonia, you can make nitrates and make explosives. That wasn't feasible synthetically until some very bright German chemists, particularly Fritz Haber, figured out how to do it, in spite of the fact that, normally you'd think, okay, we're not making much product. We turn the heat up, we make it go faster. Turns out if you turn the heat up, you make less of the product that you desire. Even though the reaction goes faster, the equilibrium point favors the reactants much more. So there were a couple of things that they did. They came up with a catalyst that let the reaction run at a lower temperature at a faster speed. And then they also came up with the idea of condensing the ammonia out and using LeChatlier's principle in that regard. If you condense that ammonia to liquid ammonia, it has, if you think about your intermolecular forces of nitrogen, hydrogen, and ammonia, ammonia is going to have the highest boiling point, so it'll be the easiest thing to condense because those boiling points are all below room temperature. So you condense it out as a liquid, and that pulls the equilibrium forward and makes more ammonia. The flip side of the bad thing about that making bombs is that you also can use nitrates to make fertilizer. So in many ways, Haber's innovation has led to being able to support a much larger population on Earth due to being able to make nitrate-containing fertilizers and grow more food. All right, so moving on now, looking at a solubility product equilibrium here involving KSP, and we're asked to figure out exactly how much lead iodate is going to dissolve in water given the KSP value of 2.5 times 10 to the negative 13th. This is, again, IO3 minus squared. The subscript showed up better on the quiz than they do in this printout of the quiz. The superscript show up better. So what we're going to do is we're going to have a ice chart. And so frequently in this unit, we're going to be talking about using an ice chart to do calculations. I think okay. And this is solid. These two are aqueous. So we're not going to have any kind of value for lead iodate itself. We start off with 0 lead dissolved and 0 iodate dissolved. The lead is going to go up plus X. The iodate is going to go up plus 2X, that 2 because of that. So X and 2X. We plug those into the KSP expression. KSP is equal to 2.5 times 10 to the negative 13th. That's going to be equal to X times 2X quantity squared, which of course is Pb2 plus concentration, that's the X, and then the IO3 minus concentration, the iodate concentration, is 2X, and we square that because there's a 2 in front of that iodate as well. So we have this little equation here to solve. That's 2.5 times 10 to the negative 13 is equal to 4x cubed. So x for that is going to be the cube root of 2.5 times 10 to the negative 13th over 4. You get a ballpark sense of those cube roots if you have a power of 10. And you're taking the cube root, usually you divide that by 3. So if I'm expecting something around 10 to the negative 4 here. Let's see, 2.5 second, comma, change sign 13, divided by 4, and then do the cube root. I get 3.96 times 10 to the negative 5th, so something in that ballpark. That would be the molar solubility, because X, if I had written it over here, it would have been minus X, right? That X value is that one, so that is our molar solubility, 3.96 times 10 to the negative 5th. Keep in mind, if you're trying to do a cube root on a calculator, you can put your stuff in parentheses and then do caret up to the 0.333, basically taking it to the, you're doing it to the 1/3 to get the cube root, in terms of punching that in somewhere. Or like, for example, if you were punching it into Wolfram Alpha or something like that. All right, now, next problem is the same situation, except now we're starting off with a 0.10 molar solution of lead nitrate using something called the common ion effect. So this is going to be a much more complicated problem, but we're going to do our ice chart just like we did before. Write our equilibrium. And we're ICE. Now the difference is, we don't really care again about the solid thing. Instead of being 0, the lead concentration is initially 0.1, the iodate is 0. Now if you think about this from a LeChatlier's principle point of view, we've added product. That's going to shift the reaction back towards the reactant, so it's going to be much less soluble. So let's take a look at what we get. So it's still, Q here is still 0, right? Because it's going to be the 0.1 for the lead plus 0 for the iodate squared. That's still 0. That's still less than the KSP value. So they're both going to go up, plus X plus 2X. So we have 0.1 plus X and 2X here. Now, if we look back at the solution to our previous problem, X was pretty doggone small compared to 0.1, and our sense tells us that this is going to be even less in this case. So I think it's probably valid to make the approximation that 0.1 plus X is equal to just 0.1. So that's our approximation approach. So we would say that our KSP, which was what, 2.5 times 10 to the negative 13th, is going to be equal to 0.1 times 2x quantity squared, which is the lead ion concentration, and the iodate ion concentration squared. So we've got this little mathematical thing here, and that means that we have 2.5 times 10 to the negative 13th divided by 0.1 is equal to 4x squared. So x is going to be equal to the square root now of 2.5 times 10 to the negative 13th divided by 0.4. So let's see what that looks like. 2.5 second comma negative 13 divided by 0.4. Take the square root of that. I'm getting 7.91 times 10 to the negative 7th. So that is smaller than we had before. If I did that in Wolfram Alpha, let me see if I can get that for you here. And so I'm going to the Wolfram Alpha website that you can't see what I'm doing there, and I'm going to type in the equation up here, except instead of 0.1, I'm going to put 0.1 plus x. So over on my Wolfram Alpha screen, I'm going to say 2.5 e negative 13 equals parentheses 0.1 plus x times parentheses 2x close parentheses caret up squared, and I'll copy and paste the Wolfram Alpha answer over here for you in just a second. I gotta adjust the scale here to get a good picture of that, and let me get a snip of that and I'll drop it on our page here. All right, let's see. All right, so here's our Wolfram Alpha output for that. You can see what I entered up here. This was what I entered was that right there. And the Wolfram Alpha results that we get is our three possible solutions here, and 7.9 times 10 to the negative 7 is the one that is a positive solution. And I think that if we look up here, we see our answer right there. Hopefully it's going to agree with that. Yeah, so it's very close to the answer we got by making that approximation that x was very small. So that's a very reasonable thing to do. Again, on your exam, since it's we're doing online exams, you're going to be able to utilize something like Wolfram Alpha. Again, I think that's a great tool to be able to use.